don't think I have ever.
Turned off the correct lights.
They're labeled and I still did something on there. Welcome everyone to Deterministic Colloquium.
I'm with you. I had no idea. I was pointing with my feet. And all this matters is it's just like my brother.
Welcome everyone to the Departmental Colloquium. It's always fun to introduce a former student. So this is Cristian Martinez-Villalobos, who some of you will recognize. Cristian got his PhD here from AOS 2 years ago, around this time. So Cristian had an interesting background. He came to the University of Wisconsin on a Fulbright to go work on theoretical particle physics, and as a master's in theoretical particle physics from the Universidad Católico de Chile. And so came here to work on particle physics, and then ended up sitting in on a class that a few of us taught on climate change and regional climate change. And in talking with Cristian throughout the class, he would ask questions that that other people would not ask, and usually they were challenging questions about ensuring that that energy was conserved and these sort of physical principles, which is what you love to see. And towards the end of that, he decided he was interested in switching majors to atmospheric and oceanic sciences, and I said I'd be happy to take him on as a student, and that worked out very well, I thought, personally. With any student, there's always every student is an individual person, and each one has, as an advisor, there are challenges that you face with any individual student. Are you ready for me? With Cristian, my challenge was trying to figure out a way to take advantage of his math skills, which he did through developing some theoretical models of meridional modes while here, and then going down and starting to work on stochastic models of climate variability with folks at NOAA Ezerol, Cecile Penland and Prashant Sargent and Matt Newman. So as part of his PhD, he developed a method for looking at state-dependent noise in multivariate autoregressive models, which was something that had never been done before. Since then, he's gone on to UCLA and is working with David Neelin at UCLA, looking at stochastic models of precipitation, which we've seen a little bit of recently. And I will say that we recently got back from, we're both in Ecuador a couple of weeks back, where Cristian won the top early career scientist, the top prize for early career scientist posters at the International Flybar Conference on ENSO for his work on estimating state-dependent noise in the linear inverse model framework. So it's always fun to. I'm looking forward to hearing what he has to say about his recent work, because every time I ask him, he kind of shrugs it off, and I get no information out of him. So I'm looking forward to a presentation now as to what he's actually been up to in the last couple of years. So welcome back, Cristian.
Okay, thank you, Dan. Thanks everybody for being here. It's always nice to be back in Madison, the best city ever. So today I'm going to talk about stochastic modeling in the climate sciences, and I'm going to show two applications, application to modeling of precipitation and a Niño Southern Oscillation. So the outline of the talk is divided in three different, I guess, points. The first part, I'm going to I'm going to talk a little bit about the basics of the stochastic modeling, and this is pretty much geared for students here. Because at the beginning, when I started doing this, I didn't have any idea about what this meant. So yeah, now I'm gonna try to give you a little review of what this means. Then I'm going to talk about why do precipitation intensities tend to follow gamma distribution. This is like my newer work working with David Neelin at UCLA. And in the end, if there is time, I'm going to talk about a thing that we're calling a linear model captures the Niño symmetry in amplitude and persistence. And this is work done in collaboration with Dan Diamond, Matt Newman, Cecil Pedland, and David Neelin. So I'm going to start by with a few slides about stochastic modeling. And as I said, this is going to be very simple, and this is geared towards students. And I'm going to give you an idea what stochastic modeling is by comparing it to the deterministic model. So a deterministic model is pretty much a model in which the future outcome of the model is completely determined by initial conditions. And an example of this is pretty much all classical mechanics, and most of simple climate models. So here, what I'm showing here is the initial condition of the probability density function of initial conditions that you may have, in which I'm assuming that we know them. We know the initial conditions with infinite precision. And then if we evolve the system, a deterministic evolution will do something like this in probability space. We're going to have a different outcome, but we're going to know it with certainty. So a stochastic model is pretty much a model in which the outcome is not fully known. Yeah. So similarly as before, if we start with an initial condition which we know all the details of the initial condition, so we know it's a delta in probability. A stochastic evolution is going to give you something like this in terms of probability. So you're going to have some spread that is going to happen even if you know exactly your initial conditions. And why does this happen? I mean, in all fairness, general circulation models, for example, they do try to simulate every processes that's going on. But even then, there are some processes that are subgrid scale that some people are pushing for stochastic parameterizations for those, for example. But you also can do like a stochastic modeling because your model can really resolve the processes, all the relevant processes. For example, ENSO. I'm going to show later a linear inverse model in which we use monthly SST data in order to calculate a model. In that case, we cannot really resolve every tropical cyclone that's going on. And maybe don't really want to know the details of every tropical cyclone that's going on, but we can do like a stochastic parameterization of what their effect in an ensemble sense is going to be. If that makes sense. And also, sometimes you can, I mean, it's super easy to resolve the processes that you want, but sometimes you don't really want to. And this is what I'm going to do in the precipitation model that I'm going to show here. In that case, we can really, I mean, should be easy to really resolve the moisture divergence. But in this case, I'm going to just do a stochastic parameterization. Is there any question so far? So, so what is stochastic modeling in a nutshell? This is a typical stochastic differential equation. It has this form, and you may all recognize this because this is pretty much the Hasselmann and Franklin-Hasselmann equation that they used to explain the mid-latitude spectrum of SSTs. And but I do know that not all of us are working in stochastic modeling, but we all know pretty much linear regression. So I'm going to say that this equation is pretty much just a linear regression. So, and again, this is geared toward the students to kind of know what's going on here. So, in a linear regression, this is something that you may have. You may try to like calculate the best fit to observation data, something like this. So the best fit is going to be something like this. But there's also going to be like something that's not really explained as linear regression. And that's similar to what's going on here, right? And this parallel can be really, really seen if we discretize the stochastic equation. As you're going to see, that's basically a linear regression in which this part looks like this, and this part looks like this, and this part looks like this. In most cases, when we look at linear regressions, we just want to look into like the mean behavior of what you can see, and that's like the typical thing that you do when you use deterministic parameterizations. This is what's pretty much doing. But in the stochastic parameterizations, we do care about the fluctuations about the typical behavior. So in a lot of applications, these fluctuations don't matter much, but in the examples I'm going to be showing, they do. So I'm going to be using forward and inverse models, and here I would like to give a little bit of a distinction between them. A forward model is the typical model in which it is a usually simplified model derived from primitive equations, in which that you know, Navier-Stokes, for example. And here in this case, the main goal is going to develop theory, less in a GCM context. And this is the kind of model I'm going to be using for modeling precipitation. And this is opposite to an inverse model in which we have the observations, and the idea is to kind of reverse engineer the model that gave rise to the observations. And this has a lot of uses. And since you're trying to generate a model that could be used as a substitute of actual observations, these models are usually a little bit more complex. This has a lot of uses, like, for example, forecasting. These are used for forecasting El Niño all the time. This is a very underrated use, hypothesis testing. If you want to do hypothesis testing on a field, this is kind of like the way to go usually. And also can be used to generate understanding of fundamental processes. So here I'm going to use this kind of model to model El Niño, basically. So this is pretty much like the stochastic modeling in a nutshell. Is there any question? Because now I'm going to go into the modeling of precipitation part as an example. Everything's okay?
Cristian, could you, I'm sorry to slow you down, could you comment on the relationship between inverse modeling, stochastic modeling, and analog modeling? Are they kind of related to each other?
Analog model is when you're trying to sample from previous realizations, right?
Yeah.
I guess there should be like a relationship. Basically, what you're doing when you have a linear inverse model is, in a way, you're doing that, I think.
Okay.
Because you're constructing your model based on past realization of the data, although I guess in the details maybe a little bit different.
Okay. Thanks.
Yep.
Just get straight here. There's two ways that model is being used here in this talk. One is statistical model,
Yes.
and the other one is physical model.
Yes.
And so you're starting with a simplified physical model in line one there, right?
Yes.
You're talking about here. So when you're backing out the model that gave rise to the observations, are you saying that you are creating a new statistical model that will be consistent with the observations and some constraint of physics, or what?
Yeah, that's a good question. So actually, I'm going to be using the forward modeling for this kind, for the modeling of precipitation example, and I'm going to be using the inverse model for the modeling of El Niño. So it's going to be two different kind of applications. Ideally, that's something that you would like to do, but I don't think that many people do that. I mean, we kind of like get the model from observations, but there should be like more of a connection also with how can we get into that model from a physical model perspective. And I think that would be interesting to do in terms of research, and I don't think many people do that.
So getting it partially to John's question as well, especially for inverse or forward modeling. For inverse modeling especially, the stochastic models are useful when there's a separation in time scale between the kind of nonlinear deterministic trajectories that would be, say, baroclinic instability and weather and whatnot, and then the low frequency response of the system that you're trying to model.
Yes.
And over those longer time scales, those high frequency variations, if you average those, the central limit theorem allows you to parameterize those as some sort of a stochastic process.
Yeah, that's
Is that the basics? But there needs to be that time scale separation.
Yeah, there needs to be a time scale separation, although people have gotten away with this kind of modeling also in systems in which you don't have that time scale separation.
Okay, but is that a I mean, ultimately, should there be that time scale separation from the, I mean, if we think of the world as being fundamentally deterministic, but because we can't exactly reproduce that, if we're parameterizing the nonlinearities of the stochastic process, does there need to be that time scale separation?
I would say if you want to be rigorous, yes. But sometimes we can get away without that time scale separation and still get like a living order behavior. Okay, so in this part I'm going to be talking about why do precipitation intensities tend to follow gamma distributions, and this is work done with David Neelin, and this is about to be submitted to Journal of Atmospheric Sciences. I realized that Sam Stechmann gave a presentation here 2 weeks ago, so I guess a lot of this new material is going to be, no? Well, but I guess it's gonna be easier to explain this kind of material, at least. So, for typical time scales, most geophysical variables that we care about are distributed not that far from a Gaussian. So you usually have like your typical behavior and you have fluctuations around that behavior. But like the extremes are not something that are something super out of the ordinary compared to typical behavior. For short time scales, for daily precipitation, for example, for short averages, precipitation distribution is highly non-Gaussian. This implies that it looks something like this, for example. As you can see, this has like a very long tail, and in this case, you're going to have extremes that are like an order of magnitude of what your typical precipitation event is. So we want to understand this behavior here, because it has a lot of societal implications. I'm going to be looking at gamma distributions pretty much here, and this is I'm going to be looking at plots like this in a log-log space. So pretty much something like this, something that looks like this in a linear plot looks like this in a log-log plot. Yeah. So first, daily precipitation distribution observations. Gamma distributions have been used since like at least the 50s in order to model daily precipitation distributions, so to characterize daily precipitation distributions. This is a daily precipitation distribution calculated from 1 minute data, Manus Island, which is an island in the tropical Pacific in the Whirlpool area. And you can see like the main features that you find in daily precipitation distribution in other locations here too. Daily precipitation distributions can be characterized by as you can see here, it rains. This is the amount of rain. This is the probability. There is a larger probability of small events, and the probability decays with size close to a power law. And this power law usually has a slope of usually less than 1, until you get to a characteristic cutoff scale size in which the distribution decays faster. And this is very important because if there wasn't this cutoff, this is how like the distribution will look like. We will have a lot of more extremes that we have currently. So I'm going to say that daily precipitation distributions can be fitted by a gamma distribution that looks like this. This tau p here is the power law exponent, and this controls the probability of light and moderate events. And PL here, which is usually known as the escape parameter, I'm going to call it the PL, the daily precipitation cutoff, and this cutoff controls the probability of extremes. So it's really important. These two values are really important. So our goals here are going to be to explain why daily precipitation distributions look like this. We would like to develop theory for these two values, tau p and PL. And here I'm going to use daily precipitation as our leading example, but the framework I'm going to show you works well for other averages as well. You can stop me at any time if you have questions. So this is my claim. My claim is that there are two ingredients that explain the distribution of daily precipitation. The first one is the distribution of total precipitation in a precipitating event. These are going to be the accumulations that Sam Stechmann may have talked about them. And this part depends exclusively on what's going on in the wet regime within a precipitating event. And the second part of the second ingredient that explains daily precipitation distributions are the distribution of the number of precipitating events in the time average of interest. That is, how many times in a day it rains, pretty much. And there's going to be a distribution of these. So in this part, this is pretty much controlled by the dynamics within an event. But in this case, what this does is that this tells you information of the aggregation of individual events. And this is going to depend on both wet and dry regime dynamics. In the dry regime, I mean what's going on between precipitating events. So here I have a little schematic. It's important that we know the difference between what is an accumulation of daily precipitation, what I'm talking here. So for example, here I'm showing, this is a schematic. Here is the precipitating rate. Here are 3 days. In day 1, there are 3 accumulation events. An accumulation is basically whatever you have between event starts and the event finishes. So you're going to have 3 events. In day 2, you're going to have no events. This is going to be a dry day. Yeah, and in day 3, you're going to have a big accumulation event. In day 3, and daily precipitation is pretty much the summation of these events in each time. So even though there are 3 accumulation events here, the daily precipitation is larger in this case. So in general, there is going to be a distribution of the event sizes here, and that's pretty much ingredient 1. And there's going to be a distribution of the number of these events in a day 2, and that's going to be given by ingredient 2 in this. Okay. So, let's go back to Manus Island again. This is the daily precipitation distribution. We can calculate the distribution of accumulations, which is the event sizes of each individual event. And this is how it looks like. So, in terms of formula, it looks pretty similar to the gamma distribution I'm using for daily precipitation here. The main difference here is that the power law range is steeper, so accumulations decrease with size faster in the power law range. So this tau, which is the power law exponent for the accumulations, is usually larger than 1. And there is also an accumulation cutoff. And as you can see here, this accumulation cutoff also controls the probability of extremes. So here, similarly to the daily precipitation case, tau is accumulation power law exponent and controls the probability of light and moderate events. And SL is the accumulation cutoff and control the probability of extremes. Yeah.
Is there a well-known formula for accumulation cutoff? Does it relate to column average temperature, or how much moisture it can hold, or?
Yes. At least in simple models, yes. So this is one of the ingredients I'm going to use in order to generate theory for how these parameters here scale. I'm going to get into it in a minute. So, as I said before, these cutoffs, so there's going to be an accumulation cutoff, there's going to be a daily precipitation cutoff, and these cutoffs are important because they control the probability of extremes, accumulation and daily precipitation extremes. This can be illustrated by looking into different accumulation and daily precipitation distributions, comparing 2 different periods in the last 40 years. Here, the blue line is the accumulation or daily precipitation distribution calculated using 1979, 1995 data, and the red line shows the accumulation and daily precipitation distribution using 1997, 2013 data. And this is done for 3 different regions in the US. And you can see that for the Northeast, it's easy to see that the cutoff has increased in the second period compared to the previous period. And same thing with the daily precipitation cutoff. So this is, in this case, the cutoff has increased by like 18% for accumulations and 15% for daily precipitation. And as you can see, this implies that the power law range gets extended in the second period, and you have something like this. Although it may not look like a lot of change in terms of probability, this little change in the cutoff results in disproportionate changes in terms of either the accumulation and daily precipitation extremes. This figure here pretty much is showing you the ratio of the probabilities. As you can see, an increase in accumulation daily precipitation cutoff gives you like disproportionate increase in accumulation and daily precipitation extremes. So that's why we care about these cutoff values.
But when you say cutoff, you mean the point at which it's no longer following a power law?
Exactly.
Okay.
Yes.
Catastrophe.
Huh?
The ultraviolet catastrophe.
I don't know.
So this is just a regraphing of the graphs on the left. The blue lines here are the percentage change. Is that right? Of the probability distribution?
It's related to that here. This is pretty much the amount of probability for an event larger than the X value, comparing the two periods. So, for example, there is like in the second periods, like extremes larger than about 100 millimeters are 3 times more likely than in the previous period. And this is also seen in global warming projections of the accumulations. So this is a similar plot as before. This shows like the ratio of the probabilities. As you can see, like the extremes accumulation increased much faster than the rest of the distribution. And yeah, this is a paper by David in 2017. So we would like to have a theory of how these cutoffs increase. I mean, it seems useful for real world applications. So here I'm going to use a simple stochastic prototype for accumulation distributions. And I'm going to show you that, at least for the accumulation part, we have theory of how this cutoff changes. And then I'm going to extend this to daily precipitation because people really care about like daily precipitation. So the model that I'm going to use is a Stechmann and Neelin model. Here we're going to divide we're going to be looking at the column moisture equation. And we're going to divide our dynamics in between wet regime, which is in the precipitating state, and dry regime. We're going to say that, and this is well constrained by observations, we're going to say that we start precipitating when moisture has increased beyond certain critical threshold, given either by convective stability or large-scale saturation. And within this regime, we're going to have two competing effects. Precipitation here, R0 is going to be the precipitation rate. Once we start precipitating, R0 is going to rain that moisture out, so it's going to be a sink of moisture. So most of the events are going to be pretty short-lived because this R0 really wants to push the moisture down to a value which is not precipitating anymore. Unless you have enough moisture convergence driving, which may resupply moisture, and if you have enough, you may have like long events and large accumulation. Here, like the important parameter that we're going to be looking at is this amplitude of moisture convergence fluctuations, and this is the kind of things that you could, in principle, resolve. I mean, using like a momentum equation, but here we're just treating it stochastically. And the dynamics in the non-precipitating state is similar. In this case, you have like moisture will generally increase because of mean evaporation source, and there's going to be mean moisture convergent, mean moisture divergent source that That's going to be really important in pushing this system to start precipitating. So if C is positive, you're going to have a lot of precipitating events because Q is going to increase until this point. If C is negative, you're not going to have that many. And I'm going to say that that's kind of like the main way in which the dry regime affects the precipitation distributions, like how often you rain is going to be controlled by this C value. And similarly, there is we are parameterizing the moisture convergence fluctuations by stochastic term.
And those two, D sub P and D sub E, are physically independent, presumed to be physically independent.
Yeah, I usually use different values for this, but we can create theory in which you can get the values from this and this in a more elegant way that I'm doing this
Okay.
here.
Okay.
But like the essential behavior is well captured by this model. So we can, like, there are ways to calculate the fraction of time you are precipitating and the fraction of time you are not precipitating. And if you know that information, you can calculate accumulations in your system. And I'm not going to go into detail of how you do that, but you get an accumulation distribution that looks like this and has the same main features as the observation distributions. So there's going to be a power law exponent, there's going to be a cutoff. The power law exponent is always 1.5 in this system, and there are a lot of systems in which this 1.5 occurs. But the main thing here is that we have theory for a cell now. So accumulations depend proportionally to the size of moisture fluctuations. So if you think of if moisture increases, you expect the size of moisture fluctuations to increase, and that implies an increase in the accumulation cutoff, which yield disproportionately increases in extremes for accumulations.
So P sub S here is the, if you go back. No, what's P sub S again? Yeah.
What do you put? P sub S?
Very bottom, first
The
pass of the
last
process.
equation.
The threshold.
Oh yeah, this is P. Thank you. This PS is the accumulation distribution. That's how I'm doing it.
Okay.
Yeah, accumulation distribution, and S is accumulation. Thank you.
Okay, and S sub L is the,
S of L is the accumulation cutoff, which in this model is proportional to this dB, the amount of driving you have in the wet regime.
So your extremes are determined by how much moisture convergence you have.
Yeah.
But only when it's precipitating.
Only when it's precipitating. Yeah.
In the real world, maybe. Okay.
Yeah. So that model is super simplified, but we can compare the distributions, the accumulation and daily precipitation distribution we get out of this model compared to observations. And this here I'm repeating Manus Island observations in which you have this accumulation distribution, this is daily precipitation distribution, and this is what we get out of the model. So the accumulation distribution looks pretty good, and qualitatively speaking, the daily precipitation distribution also looks pretty good, I would say. This is a daily precipitation distribution that we get out of integrating the previous model, like 500 years or something like that. And we also use like a little bit more realistic version of what the precipitation rate is in the previous model, in which the precipitation rate does depend on the moisture. And this is what we get out of it. This is a round precipitation model. And you also, I think both of these compare well with observations. This suggests to me that the basic physics that explains daily precipitation and accumulation distributions is contained within the model. Yeah.
So these are distributions for events, for the probabilities for all events,
Yes.
individual events.
Yes.
That have nothing to do with the duration of between events, the counts.
That's a good question. One of the accumulation distribution doesn't depend at all on the dry regime. And the dry regime is kind of what determines how many events you're going to have. But the daily precipitation will have a dependence on that. So that's one of the reasons. That's one of the reasons why accumulation distributions are easier in terms of the editing theory because in this case we also need to take into account what's going on between precipitating events.
It does look like, maybe you said this, Christian, the middle, the constant precipitation model has
Yeah.
a substantially weaker slope to the
Oh,
red line.
yeah, and we know the reason
Oh,
for that.
okay.
And the ramp precipitation model, this gives a better behavior in terms of how fast you reduce the slope of the daily precipitation compared to the accumulations.
Okay.
But still essential behavior, you can get essential behavior out of this. And it all boils down of this approximation compared to this approximation, this is more realistic than this.
So the main thing being that no matter what your moisture content, you have a constant rain rate in the middle one,
Yeah.
whereas on the right, your rain rate depends on the moisture
Yes.
content of
Yeah. So see, if you are far above the amount you need to start precipitating, you are gonna precipitate faster, pretty much. But the thing is, it's harder to do analytic theory in this case. But we have looked into like the model, and we know that the basic behavior is pretty much similar. So that's good. So the take-home message for now is that the accumulation cutoff cell is a physically derived quantity which scales with moisture availability. This implies that increases in moisture implies increases in cutoff, implies large increases in accumulation extremes. So this kind of give you like a null hypothesis of how things are going to change for accumulation. But how can we send this to daily precipitation? Accumulations are super cool in a theoretical kind of way, but people don't usually calculate accumulations in practice. People are really care about how much it rains within a fixed time interval. So here, that's why we're interested to know how can we extend this to daily precipitation.
Wait, it's not what you just showed? Wasn't that the red lines?
Yeah, but that's kind of like what the model tells you it does.
Mm-hmm.
But here we would like to have like some analytical insight on how those things depend on the underlying model. So we went into like the distribution of accumulation, which is one of the ingredients in order to explain daily precipitation distribution. The second one is the distribution of a number of precipitating events in a day, basically. And there's going to be a distribution of that may rain once, twice, 20 times, right?
In one day.
In one day. And I think the main insight that we are providing here is we are adding this into the accumulation framework in order to account for like time average precipitation distribution.
So this is most applicable to convective systems.
Yeah, I would say so. Although we have looked into like more non-convective regions, and like we may need to like reinterpret some of our terms, but like the basic shape of accumulations and daily precipitation pretty consistent with what I've shown here. So this is the part in which we go into like theory for daily precipitation distributions, and the first thing that we would need in order to extend the insight given from accumulation distributions to daily precipitation distributions is to imagine what would be the daily precipitation distribution if it rained a fixed number of times. So what would be the daily precipitation distribution if it rained only once, twice, 5 times, 20 times a day? And this is something that we can calculate in this simple model. We can calculate analytical formulas for it. And this is how it looks like, more or less. Very hard to see this. So, but this 1P1 shows what would be the daily precipitation distribution if it only rained once. P2 is what would be the daily precipitation distribution if it rained 2 times per day, 5 times per day, 10 times per day. And as you would expect, if you rain 10 times per day, you're going to have more probability for large values, and you're going to have very little probability for small values, because you're raining more times. So this is what this is basically telling you.
I don't follow that. I don't see why that's an expectation. Sorry. we have plenty of days where weak frontal passage has 5 episodes of light drizzle. So
Yeah, that's a good point. There are some assumptions here going on into this,
Okay.
and I'm going to go into how our behavior that is suggested by doing something like this is different from what you actually get.
Okay.
But what I'm saying here basically is that if it rains 10 times, you're basically sampling from the accumulation distribution 10 times. And there are going to be edge effects of that are given by like how we define what a day is. So you may have like an event that started like at 11 p.m. and ending at 2 a.m. That's going to be like the main differences here.
Okay.
But if it only rained one time, basically your daily precipitation distribution would be exactly the accumulation distribution. You're just sampling from the accumulation distribution once. And then if it rained more times, you have more probability for larger events and less probability for smaller events. So that's one ingredient. And this all can be calculated from the accumulation distribution, and this all depends only on the wet regime.
So just to be clear, there's no, it doesn't matter how long your day is. Your day is essentially infinitely long because your accumulation events, you could have 5,000 accumulation events in a day. Okay.
Yeah, and that's basically what's going to be like the difference between this approach and so this actually is going to work better for longer than daily. It's going to work perfectly for monthly, actually. So we have these distributions. We have the distribution of what it would look like if it rained only 10 times. But we also need the probability of the number of probability of a wet day having n events. So if you have a wet day, you need the probability of if it's going to rain twice, 3 times, 4 times. For this set of parameters, and this is something that we can calculate analytically. This is something that we cannot. It's a very efficient problem that involves a lot of combinatory. But for example, for this set of parameters, it rains like 18% of the time once, like 15% of the time 3 times, and so forth. And as you may think now, the daily precipitation distribution is basically the mixture of these distributions, and this being the weights of the distribution. So I'm going to say that daily precipitation distribution is this. And Pn here is given by this plot. Wn are the weights of the mixture, given by something like this. I'm gonna say that this implies that the daily precipitation, the slope of the power law is going to be smaller than the accumulation power law exponent. And you can here what I'm doing is I'm looking at this term, but I'm adding one at a time, pretty much here. So if we only consider days in which it rains once, daily precipitation distribution looks like accumulation distribution. If you consider now days in which it rains twice, you're going to lose probability here, you're going to add probability here. If you consider every day in which it rains, I don't know, 1,000 times, you're going to end up with something like this, and this is going to have a smaller slope than this one, and as a consequence, you're going to have a distribution that is well fitted by a gamma distribution.
So there's an approximate power law now,
Yeah, it's an approximate power
rather
law.
than a power law.
Yeah.
Okay.
Yeah, because people use gamma distributions, but it's not the only distribution that is used. But now I think we have an understanding of how time average precipitation distribution, how the shape of time average precipitation distribution come from. So,
How?
huh?
The blue curve in the middle there,
Yeah.
that comes from what?
That comes from, and this is going to be the part in which the dry regime enters.
Okay.
This is going to depend on the mean moisture convergence that you have. So this curve is going to be different for regions with in which mean moisture divergence dominates and mean moisture convergence dominates.
But it's not like a Poisson. You can't just do that feeding like a Poisson.
No, we tried, it's more complicated than that, yeah. I'm not gonna go into detail, but we can be quantitative. We can create theory on how the gamma distribution parameters are going to change with the dynamics of the system and also the averaging interval that you have. These are the expressions that we get out of going into the exercise that we did before. Basically, this encompasses the two ingredients that I talked about before. In this case, a double W bar and sigma W square are the mean and variance of the number of precipitating events in a day, basically. These encapsulate the effects of aggregating several storms within a day. And this is going to depend on both what the system is doing while precipitating and between precipitating events. And like the other terms here, you derive that directly from the accumulations. Here, S bar is basically the mean accumulation that you have. So you have a distribution of accumulations. This is the mean of that accumulation distribution. SL is the accumulation cutoff. And this part encapsulates like single store dynamics. And this part is how you aggregate the single store, basically. And this part depends only on wet regime dynamics. So here you have, you can break down what are the contributions to these parameters from the dry regime and wet regime, basically. And as I said, these are approximations because there are edge effects on how you define a day. So this is how it looks like comparing to, this is the analytical approximation, this is the model integration. Here I'm looking at how this varies with different parameters in the wet regime and the dry regime. Basically here, our assumptions are pretty well met. Here aren't. Still, you're going to have that the daily precipitation cutoff is basically proportional to the accumulation cutoff. You can see that the dry regime doesn't do pretty much anything on PL. And I'm not going to talk about this, but we can look into the wet and dry regime effects onto the power law exponent also that we get. So as I said, I think one of the main sides that we get out of this is that daily precipitation cutoff PL is proportional to the accumulation cutoff SL. Because this term here is pretty small for daily time scales, it's going to be more important if you keep increasing the averaging interval. So for daily time scales, basically we have shown that the daily precipitation cutoff is proportional to the accumulation cutoff. This is also seen in observations in the US. So what we get is that the daily precipitation cutoff is proportional to the accumulation cutoff, which is proportional to the size of moisture fluctuation. This implies increases in daily precipitation extremes under global warming, and basically implies that the distribution change is just going to be concentrated in the extremes. And I guess future work from this is analyze implications of this for global warming shifts in general circulation models. Theory also applies to other averaging intervals. Here I'm showing observations also for Manos Island for accumulation, 3-hour precipitation distribution, 12 hours precipitation distribution, daily precipitation distributions. And they look like this. One of the features that it has is that the power law exponent increases when averaging interval. And that's something that emerges from our framework too. And this is what the model does. So I think qualitatively speaking, it's pretty good, although our analytical results don't really apply in this range. The model does well here. Our analytical results do apply for longer than daily precipitation distributions. And these are observations for the Miami airport, like 63 years of data. And this is the accumulation distribution, daily precipitation distribution, 2 days precipitation distributions, 5 days precipitation distributions. And all this can be well represented by a gamma distribution. And this is what the model does. And like the behavior in which tau p decreases with the averaging interval that's as I said, is an emerging behavior from our model too. For long averages, this relationship apply in which basically minus the tau p value is equal to the mean number of events you have. I was going to talk about this range because it's super interesting, but I think I'm not going to be able to. So these are the conclusions, and I guess I'm not going to be able to talk about them. So, but why do precipitation intensities tend to obey a gamma distribution? Gamma distributions arise by time averaging individual accumulation events. Analytical theory explains main features of distributions as a function of climate conditions and averaging interval. PL control daily precipitation streams, and PL depends on moisture availability. So there is a prediction that comes from this, is that the prediction is approximately exponential increases in the probability of daily precipitation extremes. Future work, we like to evaluate these in DCMs, and also while the model generates sub-daily precipitation distributions resembling actual distributions, and the analytical theory that we have here is not super valid here because it would be interesting to extend this since hourly precipitation has been shown to behave differently than daily. There are people say that at hourly scales, you may have a superclass Clapeyron scaling, for example, of the extremes. But that's not something that you see in daily precipitation distributions. So I guess that's all, and I welcome questions. Yep.
It's very interesting, Cristian. One aspect I'm confused about, and it might just be because you're taking a modeling approach to gain insight, that's why it doesn't seem to jive physically, but the idea that the moisture convergence in non-precipitating intervals has no role to play in the production of subsequent precipitating intervals. Is that just a way to keep things clean in your idealized conceptual model here, or is there, does it go beyond that?
Yeah, good question. The dry regime does, I mean, the dry regime is very important. Here I'm looking just at the distribution, but the dry regime is going to be super important in how many of these events you get. And that's different. So if you have a region in which if there is a region in which you have like plentiful moisture supply, you're going to have a lot of events, but you may have the same distribution as a region in which you don't have that same moisture supply, but you're going to have fewer events, but the distribution may look similar.
Yeah, so
that makes sense.
It does. That seems to imply to me, I think there was a statement somewhere where you said this is a way of representing the fact that the dynamics in the dry periods don't matter in the same way as they do in the precipitating ones. It seems like that's not quite right.
No,
right?
no. I
That
mean,
they have an influence on the precipitating intervals as well.
Yeah, no, like the dry regime does enter into the daily precipitation distribution. It doesn't enter into the accumulation distributions.
Maybe
but
I misunderstood.
the number of accumulation distribution, like the number of accumulation events is going to be very, very well controlled by what the dry regime is doing.
Okay.
Yeah.
Thanks.
So does PL scale with the saturation vapor pressure or saturation column water vapor?
Yeah, that's a good question. I think I'm going to be able to answer that within this very simple model. Basically, like the assumptions that comes into the model works better for tropical regions in which the main moisture quantity that you care about is not really the saturation, but the moisture that you need in order to get into convective stability, pretty much, which is going to be smaller than the saturation. Yeah, but that's something that we should really look into.
So something having to do with the relationship between water vapor and precipitation?
Yes. That's something we should really, I mean, when we try to apply this to DCMs, I would like to make a partition between what comes from like convective regions and non-convective regions. Because I would say that similar threshold behavior occurs, but probably it's going to be more. This is going to be more relevant for convective regions.
And what were the parameters that PL depends on in your model?
PL. So PL depends on basically accumulation cutoff, the mean accumulation, and basically the variance of the number of events you have, and the mean of the number of events you have. In general, but this term is super small for daily precipitation, for daily, pretty much. This is not the typical way in which,
And the accumulation cutoff, Sam Stechmann showed us what it depended on, but you didn't show us that, or?
oh, yeah, I just show you the, like the proportionality there, I guess. So basically, accumulation cutoff depends on this dB square, which is kind of.
Moisture
it's-
convergence.
That's the moisture convergence in the precipitating.
Yeah, the precipitated, yeah.
Which is related to precipitable water in the column?
I mean, yeah, if that thing, basically, whatever Q you have below QC may be used as, basically this part kind of pushes you into increasing Q, or may push you into increasing Q, in which case you precipitate whatever you have in excess of QC.
The only reason I mention it is because we have observations that show the precipitable water in the total atmosphere is increasing
Oh,
due
yeah.
to climate change.
Yeah, yeah.
And therefore, that's a very important driving factor for pushing all these curves up towards extremes.
Yeah, yeah. Yeah, like the basic null hypothesis for your increases, I would say, which is something that should be quantified, but like the basic null hypothesis is going to be that this value here scales with the precipitable for moisture area.
So I'm thinking back to the, again, this time scale separation, the assumption of Gaussian forcing on this. You say this model is more relevant for a convective regime, in which case, in my mind, the Gaussian forcing is some sort of a attempt at reconciling, say, boundary layer or subgrid scale, just variations, which means that Gaussian may be reasonable in that case.
Yeah.
In the case of a system where the precipitation is controlled by large-scale, say, moisture convergence, like a frontal passage or something like that, all you would need to do to make this valid is just increase the time scale such that the variations of the dynamics become essentially Gaussian.
I would say that in addition to that, in our model, precipitation is controlled pretty much by moisture, and I'm pretty sure in mid-latitude regions, there's going to be some precipitation that's kind of unrelated to moisture too, which is going to be more complicated by dynamical factors.
But I mean, on a long time scale, what I'm saying is just that, yeah, so this is not, I mean, as there's daily precip, I could see where your assumption of just Gaussian forcing isn't necessarily appropriate for like large scale forced.
Yeah,
precip.
yeah, yeah.
But if you take a long enough time scale, why wouldn't it be controlled by moisture?
It may, but our basic model doesn't work at the time average that we want to. Our basic model works at pretty much instantaneous time. Our basic model, I mean, the basic model is resolving each event and then aggregating it.
I see.
So we're not doing a model of the already average quantity. Yes.
It seems to me that a lot of the conceptual descriptions you've had here have direct relevance to some of the transient synoptic precipitating systems in the tropics, like cloud clusters moving through the ITCZ zone.
Yeah.
And those can be observed by satellites. So this whole business about the duration of dry and wet periods is somewhat known from satellite observations when you try to apply this to convection in the tropics.
Yeah, yeah. Well, like the basic accumulation theory also predicts like a distribution of duration of duration of events and duration of the time between events, and that's whole to some extent if you compare it to observations.
Yeah, but in the tropics, it involves dynamics.
Oh, yeah, yeah, of course.
Synoptic dynamics
Yeah.
of the disturbances.
Yeah, no, here we're trying to go the simplest that we can, and still carrying the basic physics that I think explain this kind of distribution, and then try to generate analytical expressions out of it. But this clearly needs to be tested in a more complex kind of system. But I think this gives you like a reasonable more hypothesis how you can do this thing.
All right, let's thank Cristian once again. And Cristian is around the next couple of days if you have questions or would like to talk to him about this. So, thanks.
Yeah, thanks everybody.